An overview. Mathematics is a way by which we represent physical phenomena with numbers and letters. These representations, let's call them models. These models are typically some kind of analytical expression, ordinary differential equation or partial differential equation, or a set of them, which usually are functions of considered variables in the physical problem. They could be solved analytically, and that is using analytical methods. Exact analytical solutions could be obtained from these methods. However, once numbers are introduced, some approximation might be made, making the resulting value not exactly exact, so to say. For many practical problems, however, it is somewhat impossible finding an analytical solution. For this reason, we turn to numerical methods. We could solve the numerical problems with direct or iterative methods. Now, before we go into that, we should have in mind that all numerical solutions, whether direct or iterative, are truncated in some way, and this is the source of problem for many numerical methods. This truncation error stems from the way numbers are represented in a computer, the so-called floating point representation. While the set of real numbers are continuous, the set of floating point numbers are not. A demonstration of this will be given in later videos. Now back to the direct methods. The direct methods are typically characterized by requiring a fixed number of steps to obtain a solution, and this fixed number is dependent on the size of the problem. Now these methods produce quote-unquote exact solution. Now exact solution if the effects of truncation are non-existent, but then they are, and they give a near exact solution which is close to the analytical solutions with the truncation effect. So once there's truncation, it's no longer exact, even the direct methods. Also, no initial guesses are required for the direct methods. We'll see that this is not the case for iterative methods. Now the iterative methods, on the other hand, do not require a fixed number of steps, and in iterative methods, a function or an expression of some sort is evaluated repeatedly, and we hope that these evaluations would get us closer and closer to the answer. So how good the solution is usually determined by an error metric or convergence of the method. The solutions are usually approximate, although for a good number of iterative steps, an exact solution can be obtained. Some examples of direct methods include Gaussian elimination, LU decomposition, Cholesky decomposition, and some examples of iterative methods are the fixed point iteration, the Gauss-Seidel, and the Jacobi. Now, it's not limited to this, these are just some examples. Now, lastly, in numerical analysis, we should always have the following in mind when analyzing different methods. And these are the accuracy of the method. So, how accurate, how close to the actual solution, to the exact solution, do these methods approximate? And also the rate of convergence, which relates to the speed, because most of the time you are solving really large problems, and which is computationally expensive, so this might take maybe days, and we usually look for efficient methods that minimizes this time. So the rate of convergence of methods is also a metric by which we can judge or compare different numerical methods. And then lastly, the stability of the methods, because some methods, they might oscillate wildly around the particular solution, and then no matter how many times you this is especially true for iterative methods, no matter how many steps of the iterative method you take, it still does not converge to the answer. It never converges to the answer. So this is quite important. Now we'll delve into all of these concepts as the series goes on.